In problem 16, we have triangle DEF transforming to triangle JKL. Now, at first sight, it doesn't appear that there's any real obvious transformation that would merge one to the other. But if we were to rotate this 180 degrees about the origin, what we end up having is this. So if you rotate DEF 180 degrees about the origin, you have D prime, E prime, F prime here. And if you notice now, D prime is 1 unit away from the line x equals 2, and J is 1 unit away on the other side of x equals 2. E is 1, 2, 3 units away, and K prime is 3 units away. And if you look at L and F prime, those are both 1 unit away on either side of the line x equals 2. So it appears then that after a 180 degree rotation about the origin, then we can do a reflection about the line x equals 2. And in fact, if you take a look, with D is -3, -4, E is -5, 1, and F is -1, 1, that when we execute the transformation to go 180 degrees, let's just do point D to begin with, just to show the transformation there, that what we end up having is -3, -4. The transformation for 180 degree rotation about the origin is -yx. So it's 4, -3. That gives us one piece. And then -yx goes 3, 4. And that's what we end up with for D prime. The same thing for E prime, E to E prime, and F to F prime. So it's -yx, -yx. So the first one was a 90 degree rotation counterclockwise. The second, 180 degree rotation counterclockwise. Then, if you go ahead and reflect it about the line x equals 2, because D is 1 unit to the left, or to the right, J would be 1 unit to the left. E prime is 3 units to the right, F is 3 units to the left. And same with L. Since F is 1 unit to the left, it would reflect 1 unit to the right. So in conclusion, we can say that the congruence transformation that maps DEF to JKL is a 180 degree rotation about the origin, followed by a reflection in the line x equals 2. And now we move on to problem 17. Problem 17 states, which transformation is the same as reflecting an object in two parallel lines? What they're really asking here is, what is the reflection in parallel lines theorem say? And the reflection in parallel lines theorem says a reflection in two parallel lines is equivalent to a translation equal to twice the distance between the two parallel lines. In other words, if the distance between the two parallel lines is x, then each point in the preimage is going to be translated 2 times that distance, so 2x. So this point would go over to this point, the distance twice this distance. And the same thing with the other points in the preimage. The second part of the question is, which transformation is the same as reflecting an object into intersecting lines? This part of the question is asking, what does the reflection in intersecting lines theorem say? And the reflection in intersecting lines theorem says a reflection in two intersecting lines is equivalent to a rotation about the point of intersection with an angle of rotation of 2 times the angle of separation of the lines. Put simply, if you reflect a pre-image across one line and then across a second intersecting line, that double reflection is equal to a rotation about the point of intersection, and the angle of that rotation is equal to twice the angle between the two intersecting lines. So if this line and this line are separated by an angle of x, then the angle of rotation is going to be 2x. So now on to problem 18. Problem 18 deals with dilations. It says, graph the triangle in its image after a dilation with the scale factor k. So here we have P is 3,3, Q is 5,5, R is 9,3. The center of dilation is now 1,1, and the scale factor k is 1/2. So here's the center of dilation. Here are the 3 points that we're going to dilate. So the way we do this is with a equation that requires us to move this system so that this point is over the top of the origin, and these points move in direct relation to however much that point is moving. So since this point has to move to the left one and down one to be over the top of the origin, each one of these points has to move to the left one and down one before we do our dilation. If we were to dilate with the points in their original position, they would be dilated with respect to the origin, and that's not what we want. We want it dilated with respect to this point. So we have to account for this offset from the origin. Now the way we do that is by doing the following. We're going to do P prime is, let's make sure we have a right pen. Okay, so P prime is equal to, we take the scale factor, so 1/2 times the x-coordinate of our point, 3. We're going to subtract off the x-coordinate of our center. This is going to move this point to the left, getting it closer to the origin. So we subtract off the x-coordinate of our center. That's the x-coordinate of our center. And then, once we've subtracted, we've moved it over to the origin, then we dilate the point by multiplying by the scale factor. Then we have to add back the point we subtracted off. So add 1. Now we do the same thing with the y-coordinate. Take the scale factor times the y-coordinate of the point, 3, minus the y-coordinate of our center, which is 1, and then we add that back. This gives us our new point. So we have 3 minus 1 is 2. 2 divided by 2 is 1, and 1 plus 1 is 2. Then 3 minus 1 is 2. 2 divided by 2 is 1. 1 plus 1 is 2. So our new point is 2, 2. Now we do the same thing for Q. So Q prime is 1/2 scale factor times the x-coordinate of point Q. So this time it's 5 minus the center. Notice this value and this value are going to be the same because we have the same center point. So we subtracted off the center, moving this point to the origin. Then we add it back again after our dilation. Do the same thing with the y-coordinate. 1/2. The y-coordinate of our point is 5, again. And then we subtract off the center point, because the center point is still 1, and add it back. So this gives us 5 minus 4, or 5 minus 1 is 4, divided by 2 is 2, plus 1 is 3. And then 5 minus 1 is 4, divided by 2 is 2, plus 1 is 3. That gives us our cube prime. Now our last point, r prime. One-half. The x-coordinate of r is 9. Again, we have the same center point, so we subtract 1, moving it over, we dilate it, add 1 to get it back to where it's supposed to be. Then we do the y. 1/2. Then the y-coordinate of r is 3. Subtract 1, moving it to the center, dilate it, add that point back. Now we have 9 minus 1 is 8, divided by 2 is 4, 4 plus 1 is 5. Then we have 3 minus 1 is 2, 2 divided by 2 is 1, 1 plus 1 is 2. So, our final image is 2, 2, 3, 3, 5, 2. So let's go ahead and plot the points. So, our first point is 2, 2. So 2, 2. Then we have 3, 3. 3, 3 is up over the top. So there. And 5, 2. 5, 2 is there. And so we connect those. And you can see, since this side is 2, 4, 6, this side is now 3, and these sides are equally divided by 2. We can draw lines straight through each one of these points to the center of dilation, showing that they are in fact along the line of perspective or to the vanishing point, which is called our center of dilation. And that's number 18. Now let's move on to number 19.